In a previous video, I showed you how to calculate your adjacency matrix with AutoCN and then create a structure file for urea, and I also showed you how to remove the weaker interactions. But this video is going to focus on using AutoCN to create your own adjacency matrix. I'm going to go through it in a lot more detail, explain the different approaches you can use, and show how you can combine all these things together to get the adjacency matrix that you want. This should only be used in the situations where you know you're not getting the right connectivity with the domains approach. For example, using dummy atoms to the domains approach might not work as well as you want it to, so you might want to use ranges to actually find center-to-center connections. So if we open AutoCN and look at the options we have available again, we've got the domains method, the ranges method, and the solid angles method. But what do each of these actually mean? So if we navigate over to the Topos documentation, I'll put the link to this in the description too. This goes through each approach in detail. So the simplest one, if we scroll down to the bottom, is the ranges algorithm. As you can see here, it's intended for artificial nets made with nodes, so like dummy atoms. And this just calculates your adjacency matrix based on distances between nodes. It doesn't calculate any Voronoi-Dirichlet polyhedra, which we'll talk about in a minute. It just looks at center-to-center connections between your atoms. So this approach is similar to what you'd be doing if you were using the crystal maker and interaction approach, which works perfectly fine for symmetrical molecules and ions. When you've got asymmetric molecules, you might see connections as being further away when actually parts of the molecules are actually really close together. So you need some kind of description of the local coordination, which you'd get from the solid angles or domains approach. So the domains and solid angles approaches are quite similar. They both rely on calculating these Voronoi-Dirichlet polyhedra, VDPs, and these are space-filling objects which are used to partition crystal structures in quite a lot of circumstances. They give you quite a nice representation of your connectivity in your crystal structure. But what actually is a VDP? So each plane or face in this polyhedron is a boundary where all the points on one side of the plane are closer to the starting point, which is at the center of the VDP, than any neighboring point around it. So anything on one side of a face is closer to one point than any other point, and both approaches calculate these VDP. But the difference between them is how far out they look before they say this point is closer to one or another. In the solid angles approach, it's just a regular radius based off the atom that you're looking at. Whereas in the domains approach, it's quite dynamic. It adjusts this radius that it cuts off at, depending on the type of atom it originates from and the type of neighbor that it's connecting to. There's a lot more detail here, if you want to read it. But the two approaches may pick up different coordinations for this reason. The main deciding factor between which interactions to consider in the two approaches is this solid angle here. So this is a good diagram explaining it here. So solid angle, also called omega, is a good description of how large a face on a Voronoi polyhedron is relative to the rest of the polyhedron. That is also a good representation of the interaction strength. So higher omega means a larger face, which generally means a stronger interaction. So this is one of your variables that you can control while working out your adjacency matrix. You actually increase or decrease your minimum omega to consider stronger or weaker interactions. It's also important to note for molecules that the interactions between neighbors are defined by their local coordinations. So if you had a neighbor which had several connections to it from different points on your molecule, but each of those were weak connections, as you increase your minimum omega, you will cut off those interactions because they are weak when you consider them on their own. So if you increase your minimum omega over the value that each of those local coordinations contribute, then you will lose that neighbor connection. So it's important to look out for that, because sometimes you might think, well, those neighbors are closer together. Why has that been cut off before another one on a different side? It's the local coordination, so you need to look at that carefully. So let's go back to Topos and try out some of these approaches and see what results we get. So let's start with our default settings, which is domains and a minimum omega of 1.5. So this will pick up all the weaker interactions and we'll get the 14 coordinate urea we came across before. So let's check the adjacency matrix in the database entry and expand everything. So you can see we've got some valence bonds, some van der Waals interactions, and some hydrogen bonds. And our hydrogen here has a coordination number of 1 plus 5. So that's 1 valence bond plus 5 intermolecular bonds. So now let's try it with the solid angles approach. If I click solid angles, you'll also see that this bond type window gets enabled here. And this is because whatever you select for your solid angles, it will be assigned that bond type. So you won't automatically pick up all the hydrogen bonding and valence bonding like we did with the domains approach. So if I set this to valence, I'll leave the minimum omega the same, and we'll run it. So from the output, it doesn't look like there's anything that's changed. But if we go back to our database entry and look at our adjacency matrix, you can see we've got no hydrogen bonds or van der Waals interactions anymore. Our coordination has stayed the same for our hydrogen there, but we've lost all the recognition of the hydrogen bonding and van der Waals interactions. They're all just classed as interactions, and they're valence interactions. This will make it a little bit more difficult to calculate the simplified net, because previously we separated molecules by hydrogen bonds and van der Waals interactions, which you can readily do in ADS. So we go to ADS, options, topology, you can separate molecules by hydrogen bonds and van der Waals bonds. But if you change valence bonds to molecular, it would treat every single valence interaction as between separate molecules. So you'd have to go through, in this case, and identify which of these are hydrogen bonds, right click, change the type to hydrogen bonds or van der Waals. But is there a way that we can use the solid angles approach effectively? The answer is yes. The way we can do that is we can layer different bond types on top of each other. So we can start with defining the valence bonds. So if we look for the solid angles of all the valence bonds and try and find the weakest one. So the weakest one is here. These are the C to N bonds, and the solid angles of those are 26.7. So if we rerun AutoCN and we set the minimum omega to 26, you can see it's updated here. We now will only have our coordinated urea molecules. If we expand all, you can see we've got a fully coordinated urea molecule with no intermolecular interactions. We'll show this in IsoCryst as well. Those are our full molecules, but they've got no coordination between each other. So now we can add the weaker interactions on top of this. So the way we can do that is we go back to AutoCN and we can use this keep matrix button here. So that will retain the previous matrix and add all new connections to it. So if we set these to hydrogen bonds, define these as weaker interactions, so let's say a minimum omega of 10. Let's go smaller. Let's say a minimum omega of 8. Press OK, and then press run. If we now go to our adjacency matrix in here, we've now got some new interactions which are classed as hydrogen bonds, but we've retained our valence bonds from before. So if we visualize this in IsoCryst, you can see that we now have hydrogen bonds as well. In this case, they're not correct hydrogen bonds. I just guessed with the solid angles, but you can see how you'd use the approach. Let's try adding some van der Waals interactions on top. So this time we'll select van der Waals as the type. We'll keep the matrix again, and we'll lower this further to what we had before, which was 1.5. That's what we started with. We'll press run. It's picked up all these van der Waals interactions. If we look at our adjacency matrix, expand all, you can see that we've got all these extra things now. If we visualize this again, show our van der Waals interactions, we've now added those on top. So that's the keep matrix option. And that shows you one way to use the solid angles approach. So there is another way that you can have control over the solid angles approach. If we go into AutoCN again, but go to this tab instead, the VDP calculations, you can click choose atoms and it unlocks these two boxes here. So this gives you control over which atoms your VDP are calculated between. So the EL just stands for elements, so all elements. So let's say we only want to look at hydrogen to oxygen and oxygen to hydrogen bonds. If we click that EL button, it gives you a nice little periodic table. You can click all up, which deselects all those elements, and we'll select oxygen and hydrogen. And the sublattice atoms will pick oxygen. Then we can set our solid angles. We'll set those to 8. Pick up quite strong interactions. Press run. And you can see that it's only found the coordinations between the oxygen and the hydrogen. If you visualize it, you can see it a bit clearer. It doesn't really give you a correct result here, but you can see how this is another tool that you can use to get the adjacency matrix that you want. That's particularly good when you have dummy atoms, so you can actually just look at the connections between your dummy atoms and add those to the adjacency matrix using the keep matrix option. So these approaches aren't that useful on their own, but when you combine them together, you can build the exact matrix that you want. So we've covered the domains and solid angles approach. Solid angles is a bit more useful for intermetallic compounds, but I showed it for urea as an example of what you can actually do with your adjacency matrix. Let's now look at the ranges approach. So to reiterate what I said earlier in the video, this is the approach you would do when you're using Crystal Maker and the interaction program. Now I've restored my urea to its default coordination here with the domains option. We're going to see a few ways that the ranges approach can be used. So it's always good practice before we mess with our adjacency matrix too much to create a duplicate. So we'll call this one urea ranges. We'll just change a few settings to see what we can get. So if we go to AutoCN and just try ranges with all the default options, you can see it's picked up the valence interactions here that we had before. We'll end up with just our coordinated urea molecule. So if I visualize this in IsoCryst, you'll be able to see that there's no coordination between the molecules. They're just full molecules. There's no hydrogen bonds, no van der Waals. So we can actually add those on top. So the easiest way to do that is if we measure the distances between the atoms that we want to bond. So there's 2 hydrogens here. Distance from that hydrogen to this oxygen, if we use the select tool, is 2.08 angstroms, tells you down here. And because it's mostly symmetrical, that should be the same. That's also 2.08. So we can specifically add that bond range between those 2 atom types to our adjacency matrix. So if we close this and go back to our AutoCN, options, and go to our matrix tab, we know we want to keep the original matrix because we've got all the molecules coordinated. And we know we want to add hydrogen bonds, so we can set this as a hydrogen bond type. Now we need to define the ranges of the distances and the atom types that we want these extra bonds between. So I said I want oxygen to hydrogen, and I know that I want to look between 0 and 2.08, so I'll just put 2.1. That's the format that you have to type it in. If you type it in incorrectly, Topos will warn you, and it won't let you run the calculation until it's correct. So we press OK, press run. You can see the output's been updated. We've got these extra hydrogen bonds. So if we visualize this structure in IsoCryst, you can see we now have hydrogen bonds between our urea molecules. Now let's say we wanted to go further and add some van der Waals interactions on top. We could add them between the hydrogen and the nitrogen atoms, for example. So if we measure the distance between these neighboring nitrogen and hydrogens, we get a distance of 4.302 angstroms. So let's try adding those on top. We go back to our AutoCN, back to our matrix tab, and we'll say H2N. Get rid of that because we've already got those in our matrix. And we'll say 0 to 4.4. We'll call these van der Waals bonds this time. Press run. You see we've added a lot of van der Waals interactions here. So if we look in IsoCryst, you can see we've got loads of van der Waals interactions across the crystal here. So that's probably too many, but it's a good example anyway. The ranges approach is a bit more useful for ionic structures like calcite, for example. So let's just calculate an adjacency matrix for this structure. And let's say we don't want any calcium to calcium interactions and we don't want any calcium to oxygen interactions to start with. Clearly we will later. So now we've got an isolated calcium ion and an isolated carbonate ion. So if we visualize the structure in IsoCryst, we'll be able to see that clearly. Let's say we wanted to look at calcium coordinating to the nearest oxygen in the carbonate group and also the next nearest oxygen on the carbonate group. The best way to do that is by measuring distances, as we did with urea. So we'll click this calcium, click this oxygen here. So we can see that distance range is 2.357 angstroms. So let's add that on top of our adjacency matrix. So we know that we want the closest interactions, which are going to be starting from 0 angstroms all the way up to 2.357, so we'll just say 2.36. And we'll set those as hydrogen bonds, and we'll keep the original matrix, so we'll add them on top. Press run, and now if we go to our IsoCryst window, you can see we've got connections to the nearest neighbors as hydrogen bonds. Let's say we now want to add connections to the next nearest oxygens as van der Waals interactions. So the distance to this oxygen is 3.461 angstroms. Right click to deselect all the atoms. And the distance to this oxygen is 4.289 angstroms. So the next closest oxygen will be this one. So we can add this on top as a van der Waals interaction, exactly as we did for the first neighbors. So let's go to AutoCN and add this. So this time we want to keep those interactions we had before. And we know those ended at 2.36. And our new interactions are 3.461. So we'll just put 3.7. And we'll call these van der Waals interactions. Press run. Can't see that it's changed there, but if we go to IsoCryst again, show our van der Waals interactions, you can see we've now got the second nearest oxygens, and these are classed as a separate bond type. So that's quite useful for later on because we might be able to separate the structure based off of these. This isn't a real life example, this is just showing you how you can use the AutoCN module to build your own adjacency matrix. So Topos has one other quite useful tool for generating your adjacency matrix, and you can access it through IsoCryst. So I've got MOF5 here. If I visualize the structure, you can see I've already got coordination between all the atoms in the structure, but the pores in the structure are empty. So let's say I wanted to add a solvent molecule at the center. There's two ways you can do that. You can open your database entry and actually add the atom into the structure here. You can choose the element and then you type in the position the XYZ position for the atom in the unit cell. There is quite a nice easy way to do it in IsoCryst. So if I go back to IsoCryst, let's say I wanted to add an atom at the very center of the pore. We know because this is a cubic system that the coordinates are going to be 0.5, 0.5, 0.5. But an easy way to do it is to select all the structure and say calculate centroid. It will ask if you want to add a pseudo atom at that position. So if I press yes, it will add a dummy atom, this ZC, right at the center of the pore. I should add that if you click anywhere except an atom, it will select everything in the window. So let's say we wanted to add a centroid in the middle of our linker. We'd have to select one linker. So we select all the atoms that are involved in the linker and then say calculate centroid. That will add another pseudo atom here. Let's say we now try to add one at the center of our metal cluster. So we'll select the tetrahedron up here and we'll say calculate centroid. But it will tell you that that already coincides with the position, so you can't add one. So if we want to keep these dummy atoms, we can press image and save dummy atoms. So what this will do, when we close this window, you can see it's created another database entry with the dummy atoms. So if we visualize that, you can see we've got all these dummy atoms included. So one key point is that you can't have connections between dummy atoms when you're calculating with AutoCN. So we'll have to change these into different elements to actually run AutoCN, which we can do easily in the database entry. So we can change ZC at the center. We'll change that to something like barium. And we can get ZC on the linkers. We'll change that to something that isn't in the structure as well. So we'll call it gold, for example. Press save. And now if we visualize the structure, we've got our dummy atoms at the centers of our species. So now you can actually use the ranges and solid angles approach to calculate some connections between these species. Again, this is just an example of a tool you can use. This probably isn't that useful in this situation either, because when you're calculating your simplified net for your MOF, you will actually be calculating centroids for your linkers and your metal clusters, provided you've set up your structure correctly. But it shows you how to add extra things like solvents in at defined positions quite easily. I'll have a separate video where I go through a MOF calculation in more detail, as they can get quite complicated. So that was a more advanced video showing you how to manipulate your adjacency matrix by using the different methods available in AutoCN. You must take care when you use this more advanced approach that you're making sensible choices for the numbers that you're setting, because you are directly manipulating your adjacency matrix. So you don't want to do anything arbitrarily. You need to have solid reasoning for picking certain coordinations over others, particularly when you're using the ranges approach. The solid angles and domains approach are a bit more forgiving, as they're designed based off of interaction strengths. Hopefully the videos up to this point will have got you familiar with Topos and shown you how to generate adjacency matrices and structure files for any molecular structure like MOFs, ionic crystals, and molecular crystals. The next series of videos will go through how to use natural tiling to partition a tile-based structure like framework materials like zeolites.